Although robotic devices are used in everything from assembly lines to medicine, engineers have a hard time accounting for the friction that occurs when those robots grip objects, particularly in wet environments. Researchers have now discovered a new law of physics that accounts for this type of friction, which should advance a wide range of robotic technologies. The researchers say that their work opens the door to creating more reliable and functional haptic and robotic devices in applications such as telesurgery and manufacturing. The research paper, Elasto-Hydrodynamic Friction of Robotic and Human Fingers on Soft Micropattern Substrates, is published in the journal Nature Materials. Elasto-hydrodynamic lubrication (EHL) friction is the friction that occurs when two solid surfaces come into contact with a thin layer of fluid between them. This would include the friction that occurs when you rub your fingertips together, with the fluid being the thin layer of naturally occurring oil on your skin. But it could also apply to a robotic claw lifting an object that has been coated with oil, or to a surgical device that is being used inside the human body. One reason friction is important is because it helps us hold things without dropping them. Understanding friction is intuitive for humans, even when we are handling soapy dishes. But it is extremely difficult to account for EHL friction when developing materials that controls grasping capabilities in robots. To develop materials that help control EHL friction, engineers would need a framework that can be applied uniformly to a wide variety of patterns, materials, and dynamic operating conditions. And that is exactly what the researchers have discovered. The researcher says that this law can be used to account for EHL friction and can be applied to many different soft systems as long as the surfaces of the objects are patterned. In this context, surface patterns could be anything from the slightly raised surfaces on the tips of our fingers to grooves in the surface of a robotic tool. The new physical principle makes use of four equations to account for all of the physical forces at play in understanding EHL friction. In the paper, the research team demonstrated the law in three systems: human fingers, a bio-inspired robotic fingertip, and a tool called a turboreometer, which is used to measure frictional forces. These results are very useful in robotic hands that have more nuanced controls for reliably handling manufacturing processes, and it has obvious applications in the realm of telesurgery, in which surgeons remotely control robotic devices to perform surgical procedures. The researchers view this as a fundamental advancement for understanding touch and for controlling touch in synthetic systems.